Hello, my name is Mauricio Nishi. I'm an assistant professor in software engineering at the Delft University of Technology, and together with my colleagues, Eric Maziero, Rafael Durelli, and Vinicius Durelli, I will present our TSC paper entitled The Effectiveness of Supervised Machine Learning Algorithms in Predicting Software Refactoring. Refactoring is about changing the internal structure of the software without changing what it does. And you usually do this because you want to get easier maintenance, easier evolution, and etc. Refactoring got really popular after Martin Fowler's book, the one that I showed here in the slides. And since then, lots of empirical studies have shown why refactoring is so important. And I highlight this study by Kim et al. At Microsoft, and they show that refactoring helps teams to improve maintainability, readability, they see fewer bugs, there is a reduction in the code size, etc., etc. So we know that refactoring is important, and the question is, can we support developers in identifying pieces of code that really need to be refactored right now? And we see indeed lots of research on this. For example, some works try program analysis, so looking at the source code and for specific characteristics in the source code, and if those characteristics happen, then you alarm developers. Or by combinations of code metrics, let's say you look for methods that complexity is greater than 10 and coupling is greater than X, you alarm developers. Or search-based software refactoring, where you design a genetic algorithm or a search-based algorithm that tries to, for example, maximize cohesion, reduce coupling, etc., etc. And machine learning, back then when we started this in 2019, there was not a lot of work on the topic. But our main goal here was that all those techniques, they really depend on humans coining heuristics to identify what is not so good in the source code. And what we wanted to do here is take a more data-driven approach. Can we learn from real-world refactorings and use these to then recommend refactorings to developers? That's what this paper is about. And our first attempt was to model the problem as a binary classification problem. So on one side, we have methods that need to be refactored, and that we get again from real-world data. Methods that were refactored, we use those as data points. And on the other side, methods that do not need to be refactored because they are stable enough, they are good enough, developers can work with them without really needing to improve them. And hopefully, if you give all this data to a model, the model will learn how to separate between these two. And this is what we use as recommendation, whether a method should or should not be refactored. To collect this data, we need both sides, as I showed before, and finding code elements that were refactored is not so complicated anymore, mostly due to the work of Tsantalis et al. In this paper, the authors propose Refactoring Miner, which is a tool that is able to visit a Git repo, for example, and extract refactorings that have happened, and with very high accuracy. And that's what we use to extract methods and classes and variables that were refactored. And just to give you a sense of what refactorings we're talking about, those are the refactorings we experimented with, and those are basically all the refactorings that were supported by Refactoring Miner in 2019. However, identifying methods that are good enough is not so easy. We don't have a lot of work on identifying good code. So in this work, we propose an heuristic. And the heuristic is based on the repository. And if we notice that a class is being changed by developers, so developers are maintaining that class, but they're not really refactoring it, we consider that class and all its methods as good enough, because developers can evolve this class without refactoring it. And those are the ones we use as counterexamples for the model. Deciding how much you look until you decide that this method or class is stable enough is a parameter, a hyperparameter of the model. We tried with 25, 50, 100. We report the differences in the paper. But what I want you to understand here is more about the heuristic we propose. Then we need an empirical study to validate our idea, and we tried this in 3 different ecosystems: Apache, F-Droid, and GitHub. So in a total of 10,000 projects. And we visited around 10 million commits of these projects looking for refactorings, and this took us around 1,000 hours of data collection. In the end, we were indeed able to collect hundreds and hundreds of different refactorings, real-world refactorings at different levels, class levels, method levels, and variable levels. In terms of features, what do we extract from these methods and classes? Basically code metrics. So everything you can measure in a static manner, we get it. Source code metrics, process metrics, and ownership metrics. These last two are really popular also in defect prediction, so we wanted to experiment with them as well. And note that according depending on the level of the refactoring, we give more data. So if it's a method level refactoring, let's say an extract method, we give all the features at method level as well as the features of the class that the method is in, just to give a sense of context to the model. Then we just trained the models, and we did a very simple pipeline. We balanced the dataset because for some refactorings, the datasets can be really imbalanced between the two classes. We scale the features, we do some hyperparameter optimization, we do tenfold cross-validation, and we try different models like logistic regression, random forests, SVMs, and etc. In terms of research questions, we asked how accurate are those models, what are the important features, and if we train a model on one ecosystem, can it really work on another ecosystem which is completely different? So let me just highlight some of the results. So the random forest models, they were very accurate, an average of 90% across all the different refactoring operations we trained the models on. And even the logistic regression, which was kind of the simplest model we tried, showed some nice accuracy on an average of 80%. In terms of features, process metrics were also quite important, and this matches with what we observe in defect prediction work, as well as class level features when predicting method level refactorings, which basically tells us that the context makes a lot of sense as well when it comes to recommending methods that need to be refactored. Finally, when training the model on one ecosystem and trying on the other, we still see some nice numbers there. Precision, recall, accuracy around 80%, so a 10% drop from the first RQ, but still quite good. And so if I can summarize, structural metrics, they seem to be good features for refactoring prediction, not only structural features, but all those that we used. Models can do a good job even when tested in datasets that are completely different from each other, and the prediction can happen at different levels: class level refactorings, method level refactorings, and variable level refactorings. Finally, let me discuss the open challenges and things I want you to work with me in the future. So the first one is we need better heuristics to identify methods that do not need to be refactored. Those are crucial to the model. We propose these naive heuristics, so to say, but I'm pretty sure there are better ways to do this. And even if we like this heuristic, we need to create tooling to extract this in a more precise way. Right now, it's just simple code doing this. The granularity of the recommendation. Right now, the model recommends true or false, and like this method needs an extract method, but maybe you want to recommend more specific things. Like these 10 lines of code are the one that need to be extracted away. Process metrics, can we avoid them? Because in practice, they are very expensive. This is something we are seeing now at an industry partner. We are trying this work. So can we build model using even simpler features? Finally, replications. We should replicate this work to make sure that all the results are sound enough. We took the first step. I had a master student last year that replicated everything, improved our tooling, which is actually available on this Refactoring AI GitHub organization. So feel free to help me there. And that was it. That's my talk. If you have any questions, just let us know. Thank you very much.
Okay, so we're live for the Q&A. My name is Francisco Servant. I'm going to be the session chair for this Q&A. And we have Mauricio Aniche, who's going to answer your questions. So I'm going to jump right to it because you have a few questions already in the chat. The first question is, how is the balance of the two classes in percentage?
Thanks, Amir, for the question. The imbalance changes from refactoring to refactoring. I think in the paper we have a table showing per refactoring the imbalance. but during the training we balance the classes. So we basically downsample the majority class, and then we make it a 50-50. That is also something to explore. That's a big problem, I think, in this type of work, because you don't really know how imbalanced real life is, right? How many methods deserve refactoring versus methods that do not need refactoring in real life. That's something to explore.
Thank you. Okay, so the next question is, are some of the heuristics considered test case metrics? Associated to the test cases, yeah.
Not in my work, no, not right now. So we're only looking at production code and metrics, code metrics we can get from it. We added some process metrics and ownership metrics. We could also add some test metrics, but if you ask me, what I'm trying to do in future work now is to simplify the extraction of the metrics, because getting process metrics is complicated, right? You really have to mine the entire repo. This costs a lot of time. It might be very tricky in industrial partners. So we're actually trying now to do this stuff only with simple code metrics that we can get. But testing is always very important, right? And I also wonder what type of information this would add to those models. Future work, good idea.
Thank you. So you're getting multiple compliments also for great work, and thank you for stressing the importance of replications. I'm going to add my support to that. I think it's really, really important. So let's go with another question from Ari. He says that in practice, you want to focus refactoring on methods in parts of the code that are likely to undergo future change, right? So why would you refactor something that's not going to change in the future? So that bad methods in stable code is not a problem. How would this dimension fit into your work?
Good question. So I have to reflect a bit about this, because we do have some process metrics there, and they capture how often a class is changed. And so in a way, the model is also learning about the frequency of the class together with the complexity of this class. So maybe the model is actually learning this. But maybe a more qualitative work that we can do is to really look at classes that are very stable, that we know developers don't have to change it, although it's kind of ugly, and see what those models think about it. But I think related to this question is how I'm planning to integrate this in the future. So I think those models are more like to support your decision making, right? They're not like kind of orders for you, you should refactor this, but it's more like, you know, we think this needs to be refactored. What do you think about it? And then the developer takes the decision. If the developer says this is better, this is a bad idea, we don't bother the developer anymore. So then, I hope I answered that, Adi.
Thank you. So while the audience is thinking of more questions, I actually wanted to ask a question that I'm interested in. So you mentioned that you're going to you see this tool being used as flagging sections, right? That the developers may want to look into to refactor. But how would you, rank those recommendations, right? How could you help people decide where to look first?
Yeah, so something that we did not explore, but it's part of the future work, is of course those models give you a probability, right? And maybe we can use this probability to help you in deciding what to do. So we are 90% sure this method needs to suffer a extract method. And then we can use that as a way to prioritize.
Okay, thanks. So next question is, how do you identify refactoring related commits for your dataset?
Good question, Amir. So we are using Refactoring Miner, a tool created by the group of Nicolaus Santalis, and Refactoring Miner is able to navigate a commits, and the tool identifies the precise refactoring that has happened in that commit. So it's an extract method, it's a rename variable, etc. And the tool is pretty accurate. But your question raises a very interesting thing that I would love if you help me to think about the solution. So right now we are training a binary classification, right? So this means we need two classes. And finding methods that were refactored is pretty easy and accurate, thanks to that research group. But the other class, methods that don't need to be refactored, this is tricky. And in the paper, I used an heuristic, right? So if the class is changed X times without the refactoring, then I consider that code to be good enough because developers can evolve that without having to refactor it. That was my heuristic. And in the paper, I also showed that, and in the paper, I picked 50 as a number. So the class changes 50 times without a refactoring. And then in the paper, I experiment with 25, so half of 50, and 100, the double. And what I could see is that precision and recall vary. So choosing the right threshold for this heuristic is tricky, and it gives us different models. So this is what needs to be evolved in this type of research. And we have been thinking a lot on how to do this, and we were not creative enough to come up with a different approach. So if you want to join efforts with me, let me know. This is, I think, what's going to make a difference in this type of work.
Great, thank you. So you're getting some more praise for being thorough in your threats to validity, using 2 full pages. And an additional question asking you to talk about the explainability or interpretability techniques to understand why refactoring should be applied.
Yeah, so one idea that we have is to try to give you examples. For example, we are recommending this method to go through an extract method because method A, B, and C of your code base were very similar and went through an extract method. So not to explain a reason, but give you examples of previous refactorings, and then hopefully you can learn something from it. Opening the box of those models, even though we are using models that are easier to be understood if you compare to deep learning, like decision trees, for example, still, if you look at those decision trees, they are very deep. And it's very hard for a human to understand how the decision nodes really mean. So we are going more towards this idea of examples.
That's a great point. I wonder if that could even persuade people who may not think that a recommendation is valid, and then when you show the examples, then they change their mind. That would be interesting.
Exactly.
So another question related to explainability. So can you use those explainability results to basically improve accuracy on whether a code should be refactored in the future or not, according to how often it changes?
Let me read it again. Could you then? That's a good question, Ari. So if we can understand the difference between code that is stable and we don't need refactoring because it's stable from code that is actually good. I have to reflect more about this, but I think that would be hard given the data that we are feeding the algorithms. Maybe we need to feed some extra information there so that the model maybe learns how to separate between these two classes.
Okay, thank you. So I think I have more questions, but given the limited time that we have left, I don't want you to be interrupted in the middle. So I will just use these few seconds to encourage the audience to join your discussion room if they have more questions, where you can continue talking in private. And thank you again for a great presentation and great answers to the questions.
I thank you, Francisco. Thank you so much.